Greetings, we are from Group 3. My name is IRDINA and my group member is NURUL ALYSSA binti AZMAN, PUTRI NABEELA ASYIQIN, INTAN ALIA ELLEYEN and NURUL FAQIHAH. So today we are going to present KIB2016 Fluid Mechanics and Transport Process in Biomedical Engineering. So our problem statement is the value of tube diameter for the IV drip is unknown. Assume a free surface in the IV bag where P gauge is 0, located 1.78 meters above the patient's arm. The patient's blood pressure is 120/80. So the pressure in the veins is P gauge equals to 80 mm Hg. The smooth plastic tube is 1.5 meter long. For medical reasons, we need a flow of Q equals to 10 ml per minute. Assume fluid properties equal to water at 30 degrees Celsius. A. Determine whether the flow is laminar or turbulent. And B. If all head loss is in the smooth plastic tube, what size is the inner diameter is required? The theory and principle used in this problem statement is the conservation of energy that states that energy cannot be created or destroyed during a process and can only change forms. A control volume with one inlet, one outlet and energy interactions is considered as a steady flow. Thus, an IV drip is a steady flow. Hence, we can use the following equation where H pump U is useful head delivered to the fluid by the pump, H turbine is the extracted head removed from the fluid by the turbine, HL is the irreversible head loss between point 1 and 2 due to all components of the piping system other than the pump or turbine. Other than that, to determine the pattern flow, we use the Reynolds number, which is a dimensionless quantity and it depends mainly on inertial forces to viscous forces. For flow in circular pipe, Reynolds number less than 2000 is laminar flow, 2000 to 4000 is transitional flow, and above 4000 is turbulent flow.
Next is the result part where we made a few assumptions in order to solve the problem. So the first assumption that we made is the flow of the fluid is steady, where the velocity, density and pressure of the flow will not change over time at any point in space. The second one is the IV fluid is assumed to be incompressible, where the density will remain constant throughout the whole fluid. The third one is we assume that the entrance effects are fully negligible, where the flow will be fully developed. Next, we also assume that there are no band, valves or connectors, so as a result, there will be no minor losses. And in this problem, we also assume that the IV bottle is open to the atmosphere, so the pressure of the IV fluid in the bag will be equal to the atmospheric pressure and the gauge pressure is 0. We also assume that the velocity of the fluid in the bag will be the same as the velocity of the fluid in the patient's arm, where both of them are 0 since the fluid is flowing slowly. And lastly, we assume that the property of the IV fluid is the same as the property of water at 30 degrees Celsius. In the discussion part, there will be two parts that are going to be solved. For part 1, the first thing that we need to do is to convert the flow rate in milliliter per minute to meter cube per second, where the flow rate is given as 10 milliliter per minute, and when it is converted, it will be 1.67 times 10 to the power of negative 7 meter cube per second. Then, it is assumed that the diameter of the tube is 0.001 meter. To calculate the velocity of the fluid, the flow rate and the cross-sectional area are used in the equation. With the values given, we need to substitute all the value to get the RE number. The Reynolds number obtained is 133.39. So since the threshold for laminar flow is less than 2000, the flow of the fluid is proven as a laminar flow. The next part of the question is to determine the size of the required inner diameter if all head loss is in the smooth plastic tube. To calculate the head loss, we need to use the Bernoulli equation, and the pressure need to be converted to Pascal unit. Then, to calculate the diameter of the tube, we made a few iterations on the initial guess of the tube diameter and adjusting the diameter based on the head loss. For the second iteration, the diameter of the initial guess used is 0.0012 meter. So from this value, we use it to calculate the new velocity and the new RE number. These two values will be substituted into the equation to obtain the required diameter, where the answer will be 0.001 meter. For the third iteration, the diameter of the initial gas is 0.001 meter. Answer for the diameter required is 0.001 meter, where it matches the initial gas of the diameter that we used before. So therefore, the required diameter for the tube is 0.001 meter.
In conclusion, the flow in the IV drip system is laminar as indicated by the Reynolds number. The required inner diameter of the tube to achieve the desired flow rate at 10 ml per 1 minute is 1 mm. These conclusions were reached using fluid mechanics principles, including the conservation of energy and the Reynolds number criterion for flow regimes. The calculations were based on several simplifying assumptions to ensure an accurate and practical solution, which is the flow was steady and the fluid were incompressible, negligible entrance effects and velocities at back and arm, no minor losses. That's all from us. Thank you.